Okay, let's get started. This will be our first sample problem for this second topic on combined heat transfer modes. First problem is taken from the textbook by Creeth et al. Heat transfer principles and applications, and is exactly example 1.5, page 41. The problem says calculate the rate of heat loss from a furnace wall per unit area. The wall is constructed from an inner layer of 0.5 cm thick steel and has this thermal conductivity of 40 watts per meter Kelvin and an outer layer of 10 cm zirconium brick having a thermal conductivity of 2.5 watts per meter Kelvin. The inner surface is 900 Kelvin and the outside temperature surface outside surface temperature, I think this should be surface temperature is 460. What is the temperature at the interface? So here's our illustration, and we have this composite wall section, and here's the inside surface and here's the outside surface, and it says that the inside surface has a temperature of 900 Kelvin and the outside temperature is 460 Kelvin. This material, let's call it material A, and this is a 0.5 centimeter thick steel, and this is the thermal conductivity. And the second material is, let's say it's material B, which is a zirconium brick and having a thickness of 10 centimeter and a thermal conductivity of 2.5 watts per meter Kelvin. And we are asked to find what is the temperature at the interface. So what's the temperature at this interface? Okay, so this is a composite wall problem and we have a series setup. So for the solution, let's draw first. Okay, draw the thermal diagram. Okay, so for the thermal diagram, let's see, here's our point 1, and then it will have resistance, right? Starting from here, thermal, starting from this temperature or this point 1, right? So here's our point 1, and here's going to be our point 2. And from point 2 to point 3, this will be our diagram. Okay, and what else? Now it says that the temperature at point 1, this is T is equal to 900 Kelvin. The temperature at point 3, this is T is equal to 460 Kelvin. And we are asked to find this, right? What is this? The temperature at the interface. And let's just say that is T sub 2. Now in terms of resistance, this is, let's call this R sub A, and this one is R sub B. Okay, and now let's solve for, so solve for the thermal resistance, resistances. First is R sub A is equal to, our equation is this, of course the length corresponding to A, and also the thermal conductivity corresponding to A. Note that in this case there's no area that's given perpendicular to the heat flow, and therefore we'll just use this expression LL over K, and therefore our heat would be in terms of flux. I mean, it's gonna be heat flux. Okay, so now let's substitute the value. Well, now what is L sub K? What's the thickness? All right, what's the thickness of A? And we have to convert the units from centimeters to meters. That's gonna be 0.005 meters. So 0.005, so 5 divided by 100, that is 0.005 divided by, what is K? This is 40. So 40 watts per meter Kelvin, and this one is meter. So our unit would be, all right, so if you do the math, this is 1.25 times 10 to the negative 4. And the unit would be meter squared Kelvin per watt. Meter squared Kelvin per watts, or per watt. Right, now for the resistance B, then our L sub B is equal to 10 centimeter, which is equal to 0.1. Right, 0.1 divided by, what is K? So K right here, it says 2.5. So 2.5 watts per meter Kelvin. Okay, and this is 0.04. And of course the units, that's gonna be m squared Kelvin per watts. Okay, next step is solve for the total resistance. Since this is in series, then R total is just simply R sub A plus R sub B, and this is just 0.040125 right, degrees C, or Kelvin. This is right, Kelvin for now, Kelvin per watt. Okay, then what else? Then that means that if this is 0.1 and this is 0.3, the R total is equal to this 0.040125 Kelvin per watts. Okay, so if we have this, we have the temperature, since this is 900 K, this is 0.1, and this one is 460 K, then that means that we can actually solve for the heat flow. Therefore, the heat flow, or the heat flux, is, you can solve that Q, actually we'll just use this, Q is equal to delta T over R. Okay, and what is delta T? This is 460 minus 900, so recall that we have this negative sign right here, so that's just negative 460 minus 900, just to make it positive. But the physical interpretation is that heat flows from a region of higher temperature to a region of lower temperature. This one is, this should be Kelvin meter squared, right? Kelvin meter squared per watt. So this one is 0.040125, and this is Kelvin meter squared per watt. This one is Kelvin, so our units would be actually watts, because the Kelvin cancels out, so that's gonna be watts per meter squared. Okay, and if you do the math, what you get is 10,965.7 watts per meter squared. This is Q heat flux. Okay, so that's it. Sorry, that's not yet our final answer, because we're asked to find the temperature at the interface. Okay, so for the temperature, the interface, then since we have the Q, then we can solve for T sub 2. Okay, and the explanation is that the heat that enters from this surface and exits in this surface, this outside surface, is actually the same heat that passes through A and the same heat that passes through B. So in other words, the Q that enters this point 1, that's the same Q that passes across this R sub A, and the same heat that passes across this R sub B, and then exits this outside surface. Okay, so in other words, we can use this Q when solving for the temperature right here. So solving for T sub 2, then we can use Q flux is equal to, of course, negative delta T all over R. And let's say we'll use R sub A. So R sub A, we'll use this. So the temperature difference between 1 and 2 and this. And it's also possible to use this temperature difference and this thermal resistance. Okay, and let's label this from 1 to 2. And we are solving for this. So that's going to be delta T12 is equal to, of course this is negative, is equal to the heat flux times the, right, times the resistance. Of course, resistance of A only. And this delta T12 is just simply negative T sub 2 minus T sub 1, right? And again, let's just write that. And if we simplify further, what we get is what? Negative T sub 2, right, is equal to Q times R sub A, right, minus, if we transfer this negative times negative, that's positive if it's in the left, but since we are going to transpose that to the right, then that's going to be positive, then it's going to be negative. So negative T sub 1. Now let's substitute all the values. This is 10,965.7. Let's dig into this. What's per meter squared times the resistance of A, which is 1.25 times 10 to the negative 4. This is meter squared Kelvin per watts, right, minus T sub 1, and T sub 1 is 900 Kelvin. Okay, so you see that the unit will cancel out for meter squared, and watts, so you get a unit of Kelvin, and you also have the unit of Kelvin right here. So that's gonna be 898.6 Kelvin. Okay, so that's gonna be the temperature at the interface. So now let's check value, T sub 2 value, using R sub B. Okay, so therefore T sub 3 minus T sub 2, just use this. The heat flux is just equal to negative delta from 2 to 3 divided by the resistance at B. Okay, so now we are going to check if the value is the same from if the value of this if this temperature of the interface, if it's the same, if we solve for this part. Okay, it must be the same, right? So negative, so that's going to be negative delta T23 is equal to the heat flux times the R sub B, and that's just going to be negative T sub 3 is the heat flux times R sub B minus T sub 2. Okay, and this is 10,965.7 times the what is this, times the R sub B, which is 0.04, all right, minus T sub 2. Sorry, so I think we should interchange this. So that's gonna be, sorry about this, T sub 3, and this should be T sub 2 because this is what we are solving. So what is T sub 3? This is equal to 460. Okay, so let's solve that. And what we get is 800. This is 898.6 Kelvin. Okay, so that means that whether whether we solve this interface temperature, whether we use this A material or the material B, that shouldn't matter. If our computation is correct, I mean, if our mathematics is correct, then it's just gonna be the same. Okay, so again, just to do a recap on what we did in our solution is first we draw the thermal diagram because this can really help us understand the approach, or help us understand what's gonna be our approach for solving this. And then we solve for the individual resistances, and then having solved that, then we can solve for the total resistance. And if we have the total resistance and we have the temperature difference for the total total geometry, then you can solve for the heat flux, right? And once we solve for the heat flux, that heat flux is the same heat flux that will pass through this interface. Okay, so that's it. Then the next problem that we are going to do is this. Calculate the rate. Sorry, I think this should be this one. Starting from this 0.1 meter. Okay, so let's start again. A 0.1 meter thick wall having a thermal conductivity of 0.7 watts per meter Kelvin is exposed to cold wind at 270 K through a convection heat transfer. So this is through a convection heat transfer coefficient of 40 watts per meter squared Kelvin. On the other side is calm air at 330 with a natural convection heat transfer coefficient of 10 watts per meter squared Kelvin. So calculate the rate of heat transfer per unit area. So here's our wall. It's a single wall, and we have to take into account the convection heat transfer, both the inside and outside. So we are given right here, if you can just write here, it says on the other side is calm air at 330 with a natural convection heat transfer coefficient of 10 watts. Right, let's write here 10 watts per meter squared Kelvin. And right here, this is H is equal to 40 watts per meter squared Kelvin. And right here, our K, thermal conductivity, is 0.7 watts per meter Kelvin. Okay, so this is a combined conduction convection, which is simply a parallel, a series type of heat transfer problem. Okay, so for the solution, again, for the solution, first let's solve for or draw the thermal diagram. Right, so first from point 1 to point 2, that's gonna be this resistance, and then let's write this is point 1, this is point 2, and from point 2 to point 3, and this one is from point 3 to point 4. So right here it says that we have a temperature already of 270 K, and right here we have a temperature of 330 K. So this one will be, let's label this as R sub A for the convection, or let's just write, you can use R sub C, but that doesn't matter. Let's just write here R sub A, R sub B, R sub C. Alright, so this one is for convection. Let's write it here. This is for convection. Right, so this is for convection, and this one is conduction, and this one is for another convection. Alright, so the next step is to solve for the individual resistances. So R sub A is equal to, again, take note that we don't have the area that is perpendicular to the heat flow. So our R sub A would just simply be 1 all over H. And of course, that's going to be H related to A. So this will be the value. Okay, so 1 all over 40, then this will be this will be 0.025 Kelvin, again, meter squared per watts. And for R sub B, this is 1 all over, L over K. Of course, K sub B is equal to 0.1. The thickness is the 0.1 thickness time divided by this K. So this is 0.7, which is equal to 0.143. So Kelvin meter squared per watts. Then R sub C is 1 all over H sub C is equal to 1 all over 10. What is it? 0.1 Kelvin meter squared per watts. Okay, now that you have that, solve for the total resistances, or the total resistance. So R sub T is just equal to, since this is a series, then R sub A plus R sub B plus R sub C. If you add these three values, what you get is 0.268 Kelvin meter squared per watts. Okay, now once you have this total, so it's just like this. So here's our point 1, right? And here's our point 4. So here's our R total, which is this, and the difference, the temperature is 270, and here is 330. Okay, so solving now for the heat flux. Solving now for the heat flux, this is Q, this, and then delta T, of course, delta T from 0.1 to 0.4, and of course that's going to be the total resistance. This is 330 minus 270, right? 330 minus 270. Actually, since this is higher temperature than the point 1, then the heat flow should be going this way. Okay, so that should be final minus initial, so this should be minus 270 minus 330, okay, and divided by the R total, and this is 223.88 watts per meter squared, of course in this direction. Okay, so if we do a recap on what we did, here's our problem, and it's a combined convection, conduction, and another convection right here. And since we have this values for the temperature, 0.1 and 0.4, and we have this heat transfer coefficient as well as the thermal conductivity, the material, the thickness. Right here we also have the heat transfer coefficient, so therefore you can actually solve for the resistances. So the first step that we did was to draw the thermal diagram, and we draw that in having a series connection. Okay, and then we solve for the individual resistances. We just simply use the formulas, 1 over HA or L over K sub B, and if you recall that sometimes the area is given, sometimes it's not given. So if it's not given, then we shouldn't include it here. So we will just carry the units. Okay, so once we have this, once we substituted all the values, and we can solve for the individual resistances. And once you have this, then you can solve for the total resistances. Now, if you have the total resistance and you have the first and final point, of course, under consideration, if you have these total points or the outermost points, then you can solve for the heat flux. Now, the heat flux is actually the heat flux that's going from 4 to 3, and it's the same heat flux from 3 to 2, and it's the same heat flux from 2 to 1, and it's the same heat flux that exits this. Right, so that's going to be the value, and I just noticed that the temperature at 4 is higher than temperature at 1, so therefore the flow direction should be going leftward. Right, so I guess that's enough for this video. We'll just continue solving some more problems in the next video. So see you.